Hello and welcome to our webinar today. Today we will be discussing the topic implementation of high power modules with Fronius inverters. Joining me today is my colleague Mohammed Sidat. He's a technical sales advisor based in Joburg, South Africa. He's taking care of the Southern African market. And myself, David Mwangi, I'm the technical sales advisor for the Eastern African region. I'm based in Nairobi, Kenya. And today we will be taking you through the content of the webinar. So when it comes to high power modules and the developments that are going on currently as far as modules are concerned, we are going to look at what are the key differences to the existing module types, what you should take into consideration when you're connecting these modules to Fronius inverters. Then we're also going to examine the kind of losses that can be expected when you're using these higher power modules. Then I'll hand over to my colleague, Mohammed, who will do a live demo and take you through the string design using one of our configuration tools. So as usual, if you have any questions during the course of this webinar, please post your questions in the questions area, and we will do our best to answer your questions and give you relevant feedback. So let's get started. In terms of the modules that have been coming up, we have seen modules that are going above now 400 watts, and these are what we are referring to as high power modules. Typical cell sizes are now in the region of 10 inches to 12 inches. And the module current also is increasing to above 12 amps. So the major module manufacturers in the world, including the ones listed here and many more, such as Trina, Jinko, JA Solar, as well as Longji, have now in their product portfolio modules that are way above or well above 400 watt peak. So in terms of the classification, we can boldly classify modules into three major classes. We have what we are referring to here as the standard modules that go up to approximately 350 watt peak with an MPP current of about 10 amps approximately, not exceeding that. And the size of the module in the region of 100 by 170 centimeters. In terms of application, this is a module that can be used for all types of installations, whether it's rooftop or free field installations, because it's quite easy to handle these modules. And also in terms of compatibility with inverters, this has been a module category that has not had any major issues with string inverters. The other class is what we are referring to here as the type A, and these are modules that are now approximately 400 watt peak. In terms of IMPP current, is now in the region of 12 or 13 amps. And the module in size, as you can see here, is slightly bigger than the previous class, which we refer to as the standard modules. So this one is about 110 by 175 centimeters. And likewise, this module, because still the current is not that high, can be used easily in all market segments, whether you're talking about commercial or residential rooftop installations, or maybe ground mounted or what we refer to as free field installations. The third class is what we are referring to as the type B modules, and these are modules now that are approaching or going now above 550 watt peak, with a current in the region of 13 amps all the way to 18 amps. And the module dimensions, as you can see here, slightly bigger, significantly bigger actually, compared to the other two classes, with a width of 120 by a length of 230 centimeters. So because of these dimensions, the application of this type B module will be quite limited when it comes to rooftop installations, because handling this kind of PV size or module size on the rooftop will become quite tricky. So therefore, as far as the installations currently with PV modules are concerned, this type A of modules up to 400 watt peak are quite ideal at the moment, and you're not going to have major problems with this category. So then the question is how to combine these different modules with Fronius inverters, and we are going to look at that. So how do you then qualify a module to be used with an inverter or a Fronius inverter for that matter? So there are a few checkpoints that you should go through to decide if a certain module can be used with an inverter that you intend to install. And number one, you have to check if the DC input current per string, the max DC input per string of the inverter is greater than the short circuit current of the module that you have. If the answer is yes, then the module can be connected directly to the inverter. And if the answer is no, then direct connection might be impossible. So in this case, you might want to consider a pre-combined connection, maybe like using the DC combiner boxes. So why therefore should the ISC of the module not exceed the IPV max of the inverter MPPT? So just to understand this short circuit of the module, this would happen during only worst case scenarios, and this therefore would indicate a failure. And when this short circuit happens, all relevant inverter components must be able to withstand this possible failure or defect. In addition to that, the DC disconnector that is, for example, integrated in the Fronius snap inverter must be able to safely cut off from this short circuit without the DC disconnector itself failing. The number two criteria that would qualify or disqualify a module for use with an inverter is to check if the maximum input current of the inverter MPPT is greater than the maximum current of the module at maximum power, or what we refer to as IMPP. If the answer is yes, then this can be comfortably connected to the inverter without any power derating. But if the answer is no, then you could still, to a limited or to a certain extent, still use this module with the inverter, but a bit of power derating will be expected. When it comes to the short circuit max current, how you can do the comparison to be able to know if a certain module will be compatible to the inverter that you want to use, we have here an example of a Simo Gen 24 Plus. This is the Fronius hybrid inverter. And we also have a snapshot here of a Jinko 440 watt module. So as we can see from the Jinko module, we have a short circuit current of about 13.73 amps. But when you look at the Gen 24 MPPT, we can connect, for instance, to MPPT1 a maximum of 25 amps. So your current to this MPPT has to be either less or equal to 25 amps. When you compare to a Simo snap inverter, Simo 5 snap inverter, you can see that you can connect per terminal a maximum of 33 amps, and therefore this module can be directly connected to a Simo 5 snap inverter without any problems. Another comparison here is, something we can check is how you can connect several modules, or this we're referring to as high power modules, with the currents ISC going upwards of 13 amps. So for instance, if you have a Simo Gen 24 10 kilowatt inverter, and you have several strings that you want to pre-combine, you might find some limitations here because, for instance, by combining only two strings, you're going to find that the string current is going to go above the maximum rated MPP current of the inverter, which is 25 amps, but only two strings with these 13 amp modules are going to give you 26 amps. So you could still connect directly to this inverter, but just a bit of power derating will be expected. Therefore, with these high power modules, the use of string combiners with an inverter like a Simogen 24 Plus is going to be a bit limited. Also, another comparison is in terms of the maximum input DC current of the inverter MPPT. So in terms of also looking at the Simogen 24 Plus, you can see that the usable MPP input current for MPPT1, because this inverter has two MPPTs, you have MPPT1 with 25 amps and MPPT2 with 12.5 amps. But if you look at the same module that we are considering, this Jinko module with 440 watt peak, the MPP current at 25, or these are the standard test conditions, will be about 13.05 amps. And therefore, you might have a problem if you are designing a system with two orientations, and one orientation is connected to MPPT2 that has only maximum current of about 12.5 amps. And therefore, still you could connect this module there to MPPT number 2 here, but a bit of power derating will be expected. But for MPPT1, this is not going to be a problem at all. Looking at a Primo snap inverter, the same issue. This inverter would have two MPPTs, and each MPPT is taking only 12 amps. So therefore, if you're connecting this Jinko module with 13.05 amps to this MPPT, then a bit of derating there will be expected, but you're going to look at what this means in terms of the actual yield losses. So the Fronius R&D has done quite a bit of work to study the effects of using these higher power modules with our inverters. And they have come up with a white paper with the title Economic System Design with the Gen 24. And this looks at what happens if you connect these higher power modules, for instance, to a Primo Gen 24 Plus. As we saw, the IDC max for the MPPTs is in the region 22 amps and 12 amps. If you do two strings with MPP current at standard test conditions of 13 amps, this would mean that considering MPPT number 2, you have exceeded the allowable current by about 8.3%. However, even in places with the highest irradiation, the actual yield losses with this kind of connection are going to be less than 0.2%. So it's a question of you deciding whether this 0.2% in yield losses really makes a lot of difference or not. The same calculation can also be done for the Simo Gen 24 Plus, the 10 kilowatt inverter. So this one comparatively has 25 amps for MPPT1 and 12.5 amps for MPPT2. So the reduction in the annual yield, if you're using also this kind of module with 13 amps, is going to be only about 0.1%. So looking at this energy loss analysis, the annual loss if the IDC of the PV generator exceeds the maximum power connectable to the inverter MPPT by only 8% is actually very low, and for quite a number of reasons. So reason number one is that very high and direct radiation to a PV array is quite rare, or very rare in some cases. And this can be due to weather, time, orientation, as well as the season of the year that you have. And therefore, because of these conditions, the theoretically possible energy, or that can be produced from the PV module, is achieved quite rarely in terms of achieving or hitting the 100% rating of the module. And therefore, this means that even with current limitations, there are hardly any yield losses as far as the actual production of the inverter is concerned. So, but to summarize this, we would say that if the PV generator current does not exceed the IMP max of the inverter MPPT by more than 15%, then the annual energy loss would be below 1%. So this is also a very important statement to always remember. Remember that also that it's possible to oversize all Fronius inverters by a factor of even 50% in some cases. And therefore, when you do oversize an inverter, you already are increasing the connectable current on the DC side, but that has no effect also on the inverter warranty as far as if any issues are caused by the DC connection. Having said that, let's look at the consequences of using these higher power modules with different Fronius inverters. So let's look at, for instance, snap inverters for residential use, and we are looking at the Primo 3 to 5 kilowatts. Then we have the Primo 6 to 8.2 kilowatts, as well as the Simo 3 kilowatts up to 8.2 kilowatts. The ISC max per string is as shown here for the Primo 20 and 33 amps for the Simo. In terms of the current per MPPT, because all these inverters have 2 MPPTs, we can see that the Primo 3 to 5 has a lower current handling capacity per MPPT at 12 amps, and then the Primo 6 to 8 with 18 amps per MPPT, and then the Simo 3 to 8 also slightly lower at 16 amps per MPPT. What this therefore means when you are designing or sizing a system using the typical 400 watt module with 13 amps would mean that if you are to connect this module directly at string level to the inverter, the Primo 3 to 5 kilowatts, you would expect very little energy derating. But for the Primo 6 to 8 kilowatts and the Simo 3 to 8.2 kilowatts, then the combination between the 13 amp module and these 2 inverters would actually be perfect. When you're connecting this 13 amp module to the Primo 3 to 5 kilowatts, because there is this bit of expected derating, you can connect the 2 MPPTs in parallel to mitigate this derating of power. However, for the Primo 6 to 8 kilowatts and the Simo 3 to 8 kilowatts, the paralleling of the MPPTs is not going to be necessary. As we can see in this figure below, this is how you would connect the 2 MPPTs of the Primo in parallel. So it's just a question of placing a jumper from the second string connection of MPPT1 to the first string connection of MPPT2, and therefore that makes them share the power that is coming from the DC combiner box that you have. In terms of the commercial installations, looking at Fronius inverters that are used for different commercial installations, here we have the Simo 10 and 12.5 kilowatts. We also have the Simo 15 to 20 kilowatts, as well as the Echo inverter. So the Echo is available in 25 and 27 kilowatts. The short circuit current maximum per string for the smaller Simos, that is 10 and 12, is 33, as well as the bigger Simos, 33 amps. But for the Echo, we can see is much lower at 15 amps. In terms of the MPPT current possible, that is maximum for the Simo 10 to 12 is 27 on MPPT number 1 and 16 amps on MPPT number 2. For the 15 to 20 kilowatt Simo, we have 33 for MPPT 1 and 27 amps for MPPT number 2. But for the Echo, we see that the power handling capacity for just the single MPPTs that is there is quite nice at 47.7 amps. What this means in terms of designing systems with 400 watt peak modules that are giving you an output at maximum power of 13 amps thereabout, is that for all these snap inverters for commercial installations, you have no problems at all connecting these as direct strings to the inverter. However, if you now go on to start using the 550 watt peak modules going up, and the output current at maximum power is now 18 amperes. For the SIMO 10 and 12 kilowatts, you are going to have the possibility to still connect directly to the inverter, but a bit of energy derating is going to be expected, because we can see here for MPPT number 2, the maximum power connectable is 16.5 amps, but MPPT number 1 is still going to be able to handle this size of module quite nicely. When it comes to the SIMO 15 to 20 amps, the connection is also pretty good for 18 amp modules, because we can see the power handling or current handling capacities per MPPT are quite nice. And also in terms of the string current is also very nice. When it comes to the Echo inverters, the 27 and 25 kilowatts, when you're using the 18 amp modules, the direct connection, therefore, in this case, is not going to be possible. So this is very important to note. And alternative design possibilities for both the SIMO 10 to 12 kilowatts and SIMO 15 to 20 kilowatts is going to be able to do this also by parallel connection of the MPPTs, especially for the 10 and 12 kilowatt SIMO. But for the Echo, in this case, if you desire to use an 18 amp module, you're going to require a DC combiner box. So with a DC combiner box, we also have the DC connector kit that you're able now to connect this DC power using only plus and minus to the inverter with this DC kit that you order from Fronius. Also looking at the Gen 24 Plus, what are the implications of using these higher power modules? We have here 3 examples also. We have the Primo 3 to 6 kilowatts. We have also SIMO 3 to 5 kilowatts and also SIMO 6 to 10 kilowatts. In terms of the short circuit current maximum per string, we have 25 amps across the 3 inverter categories here. And the maximum power connectable to the MPPTs of the inverters, we can see, as you already know, the Gen 24 Plus also has 2 MPPTs. MPPT number 1 is taking for the Primo 3 to 6, 22 amps, and the second MPPT 12 amps. And then for this SIMO 3 to 5, it's 12.5 amps per MPPT. And then for the SIMO 6 to 10, we have 25 amps for MPPT number 1 and 12.5 amps for MPPT number 2. So when you're sizing an installation using the 13 amp module, across the 3 MPPTs, the only challenge you'd have, or across the 3 inverters, the only challenge you'd have is only with the second MPPT. And therefore, like I said, if you are designing a PV installation with the arrays with 2 different orientation, and you intend to connect one orientation to the second MPPT, here you might have a bit of power or energy derating happening. However, please note that connection of the 2 MPPTs within the inverter in parallel is still possible, so that all the power that is generated or all the current that is generated on the DC side of the array is handled by the 2 MPPTs together, and therefore you're able to safely use all the generated power by the 2 MPPTs. Now we look also at the consequences as far as the Tauro inverters are concerned. As you know, Fronius now introduced what you're calling also higher power commercial inverters that we are referring to here as the Tauro. So we have this available as 50 and 100 kilowatts. In addition to that, we have split these inverters into 2 major categories. Category 1 is what we refer to as the pre-combined version of the Tauro. And category number 2 is what we refer to as the direct version of the Tauro. So when it comes to the pre-combined version of the Tauro, this can deal with any version of or any type of module in the market, because the DC power is pre-combined in a DC combiner box before it is connected to the inverter. And then when it comes to the Tauro Direct or the Tauro D, Here we have a bit of limitations when it comes to the 18 amp modules, because in no case should the IMP max per string be exceeded. But you see here that because the maximum current per string of the Tauro D is just about 14.5 amps across all the Tauro inverters, then the connection of these 18 amp modules will not be allowed, or is not going to be possible. So in this case, if you are going to use higher power modules for commercial installations with the Tauro, we do recommend that you go for the Tauro P, that is going to offer you a lot of flexibility in terms of connecting this DC power. As you can see with the Tauro D, you can achieve quite nice or quite high string connections. For Tauro D, Echo D 100 kilowatts, you can do up to 15 strings directly. And this can handle up to about 3 by 75 amps. And then for the Tauro Echo 50D, this would handle up to 8 strings directly to the inverter, handling maximum 2 by 75 amps. And then the Tauro Standard. So there's a difference between the Tauro Echo and the Tauro Standard. So the Tauro Standard would have 3 MPPTs, and the Tauro Echo has only 1 MPPT in this case. But the Tauro Standard 50 kilowatt direct version can be able to handle, in this case, up to 9 strings connected directly. As you can see here, per MPPT, we have MPPT 1 taking 36 amps, MPPT number 2 is taking another 36 amps, and MPPT number 3 is taking maximum 72 amps. So always pay attention to the datasheet of the inverter and the datasheet of the module that you are designing with. But I think my colleague Mohammed will be able to shed some more lights in terms of the string design and how you can achieve and confirm that the inverter you're going to use can be compatible with a particular module. So down here we have the string connection area of the Tauro Echo. So and the Tauro standard direct version as well. So these are going to be provided with MC4 plugs, which is quite different from the snap inverters, whereby you need to connect the strings directly to the terminal block area of the snap inverter. So the connection of strings directly to the Tauro is going to be quite fast and easy in comparison. So that brings me to the end of the first section of this webinar. So I will be handing over to my colleague Mohammed to take you through the remaining bit of it. So Mo, if you can join us from here.
Thank you, David, for the very informative part of your presentation. For my part, I'll just be taking you through a little demo using our Fronius Solar Configurator program. You can also, choose to use the Fronius Solar.Creator program as well to do your string planning when it comes to using Fronius inverters. So what I've done here is I selected a panel, which is a GA solar panel. We are going to look at one of the bigger panels. So in this case, I chose the 550 watt panel. And let's just have a look at the data sheet. Okay. So yeah, if we press the information tab, we can see the data sheet of this module. And here we can see what we really want to look at is your MPPT current. Here we can see it's about 13 amps. And as my colleague David was mentioning about the 13 amp modules, we will now have a look at how you can actually string them. The second important parameter here is that MPPT voltage. Here we can see it's 41.96 volts at your standard test conditions. And we also got your short circuit current, which again is very important, and your open circuit voltage. Okay, the next important parameter you need to select is the number of PV modules. I prefer to leave this as 0 initially, and then add in the figures once you get recommendations here at the bottom of the screen. The module temperature, this is very important. So remember, the lower the temperature is, the closer your PV module is to its short circuit, let's call it your short circuit voltage. Sorry, your open circuit voltage level. So at about 0 degrees, -1 degrees, that's where the panel is close to its maximum open circuit voltage level or rating. So for example, if you are planning to do an installation in South Africa, we don't really see temperatures going below, -5 degrees. So my recommendation is to set -5 degrees as a minimum. If you, for example, you in Nigeria, I don't think you'll be seeing -5 degrees. You can maybe, instead of putting -5 degrees, put 5 degrees Celsius. Okay. In terms of the maximum temperatures, again, in South Africa, my recommendation would be, 80 degrees Celsius. The reason for that is the maximum temperature your module will usually be around 12 o'clock or 1 o'clock in the afternoon. And if your ambient temperature is 40 degrees Celsius, which could be the maximum, okay, it's a good approximate to take of the maximum temperature of the module is to multiply that figure by 2, so we get 80 degrees Celsius. But if you know this panel is going to be installed in an area that maybe reaches 45 degrees Celsius, my recommendation would be to, multiply that by 2 and change this to 90 degrees Celsius. Okay, the next question the program asks you is the power gain. Okay, in this case, I'm selecting 0 because this is not a bifacial module. Okay, so I'm going to ask you for your country. The next question is your series. So when it comes to the series, this refers to what Fronius inverter are you using. So in this case, we want to, use a Taro. Once I've selected that, the next question will be is what type of Taro do you want to select? Okay, remember with the Taro, we have multiple versions of the Taro, as you can see over here. I'm going to go with the 100 kilowatt, three-phase inverter, and D stands for the direct version. So that means you want to connect your PV modules directly to this inverter itself. The next important question is obviously your inverter ratio. In this case, I'm selecting a minimum inverter ratio of 80% and a maximum of 150%. The reason why I'm choosing 150% over here is the Fronius Taro inverter can take a maximum DC of 150% of its DC power rating. Okay, the questions over here is just referring to, does the system have storage or not? In this case, we're doing a normal grid-tied system, so no storage is selected. Okay, once I've selected all these parameters, I'll then get a whole bunch of suggestions. Okay, for this example, I want to choose the highest inverter ratio recommendation that I get from the program. So in this case, the most amount of this particular type of module that I can install on this inverter is this last column. So it's this block over here. If I select that over there, we can see that the number of strings, okay, well, before we get into that, remember this inverter has one tracker only, okay? However, this tracker is divided into 3 components. We call that component PV1, component PV2, and component PV3. However, PV1, PV2, and PV3 feed into the same MPPT tracker. That's very important. Okay. With a 100 kilowatt Taro, input PV1 can take up to 8 strings, PV2 can take up to 7 strings, and PV3 can take up to 7 strings. So if we add them together, we can see that the Taro 100 kilowatt D version can have a maximum of 22 strings connected. Okay, in this case, the program suggests that I should rather go for 4 strings on my first part of tracker 1. Okay, and here I have 4 strings with 17 modules per string. Okay, here we can see that we are not exceeding the open circuit voltage. And we also fall within the MPPT voltage, which is very important as well. Okay. What's also important to note is that we do not exceed your short circuit current rating of the inverter. And here we can see your MPPT power of these 4 strings of 17 modules is about 37.4 kilowatt peak. Do we need a string fuse? Yes, we do need a string fuse. The reason why we need a string fuse is because we have more than 3 modules. Well, sorry, we have more than 3 strings per track, which in this case is obviously more than 3 strings. PV2, 5 strings, 17 modules each. Again, we're not exceeding the ratings. In this case, I have slightly more power on this PV2 compared to PV1. Again, we do need string fuses. We don't need a string combiner, and there is no loss of yield. PV3 is suggesting that I have 5 strings of 17 modules each. Here we can see we're not exceeding any parameters of the inverter. We again require string fuses, no string combiner required, and no loss of yield. Okay, so what's important to note here is also the inverter ratio overall is 131%, and technically we're connecting about 131 kilowatt peak of modules to 100 kilowatt inverter system. Okay, we can always then create a report. Okay, the system will create a report, and then yeah, you can take the report and give it to your client, or do further analysis with it. But here we can see all the parameters I was discussing. Okay, so as you can see, the 13 amp modules on the market, MPPT modules, 13 amps, do work with the Fronius Tyro 100 kilowatt D version. And here we can see we're actually using a 550 watt PV module, which is quite big. Okay. Okay, we can also, have a look at, other Tyro inverters in the range. So maybe you want to look at the 50 kilowatts. We just select that. As you can see, once we select that, a few things changes. But yeah, we try and, in this case, I want to show you the highest inverter ratios. So with this application, we were able to achieve 150% inverter ratio with a 50 kilowatt Fronius inverter, which means that I had almost 75 kilowatt peak attached to it. And here we can see on PV1, we've got 4 strings of 17 modules, and PV2, we've got 4 strings of 17 modules. What's very important here is that you can see all the string lengths are the same. The reason for this is that we have one MPPT tracker, and we really need to keep the string length the same. Remember, you can only have varying string lengths when you have more than one MPPT tracker. Okay, so let's have a look at our eco range. So we're still going to use the same module, 550 watt, but now we want to look at the eco 27 kilowatts. Okay. So we select that. Remember, with the eco 27 kilowatts, the maximum percentage utilization is 140%. So yeah, please just take note of that. Okay, once we do the selections, the highest inverter ratio I can get is 136% using these modules. And here I've got 4 strings of 17 modules each. I do need string fuses. Okay, I don't need a string combiner, and there is no loss of yield. Okay, yeah, so you can definitely have a look at this program, play around with it, and see whether your module actually works with the inverter before you actually go and order those modules. Okay, so just to summarize, for the residential sector, our residential inverters can easily be combined with 13 amp modules. In the case that you are, for example, using a primal inverter that's between 3 to 5 kilowatts, you will get minor energy losses, as my colleague David showed you. For the commercial sector, the snap inverters can deal very well with all different types of modules. Eco snap inverters require DC connection kits when using 18 amp modules. The Tyro P can deal with almost all modules on the market, and the Tyro D is ready for almost all 13 amp modules on the markets. Okay, that's it for today's webinar. I do encourage you to ask any questions in the chat tab. Otherwise, have a good day, and we'll see you in another webinar. Goodbye.